The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
All right, okay, let's start. 1690, numerical methods. Okay, because people are asking like 540 questions. Local accuracy and global accuracy. Again, this is an important distinction between local accuracy and global accuracy. What is the distinction? What is that we ultimately want in a numerical method? Do we ultimately want global accuracy or local accuracy? We ultimately want global accuracy, right? Local accuracy actually doesn't, if a scheme only has local accuracy, it's useless, right? It is useful only if it has global accuracy. Global accuracy means the solution using numerical method actually matches the true solution as my delta t goes to 0. So global accuracy is what we want. But how can we analyze global accuracy? We can only look at global accuracy when we apply the scheme to solve a differential equation, right? Is there a way to show global accuracy without actually coding it up and solve a particular differential equation? Is there a way to show global accuracy without applying its definition? Okay, so global accuracy means V at a particular time, right? Converges to U at T. So VT is the numerical solution. UT is some true solution I may or may not know depending on what equation it is. So this is global accuracy. Of course I can check global accuracy by applying my scheme to a particular differential equation. But is there a way I can know if a scheme is globally accurate or not without applying it? Yes? Yes, that's the answer I'm looking for. If the scheme is locally accurate, which is also consistent, and it is zero stable, then I know whatever differential equation I apply to, I'm going to get global accuracy, right? This is a good thing because it is independent of what differential equation I look at, right? If I can show local accuracy, which doesn't require me to implement anything, right? I just do what? How do I show local accuracy? Taylor series, right? You can show local accuracy by applying Taylor series analysis. And can you also show zero stability without doing implementing anything? Exactly. You can plug in du dt equal to 0. So zero stability is if a scheme can solve this, right? Usually, whatever scheme you have, you plug in this trivial differential equation into the scheme. You can analyze its behavior analytically. You can plug in an exponentially growing solution to see if that solution is possible. If an exponentially growing solution is possible, then the scheme is not zero stable. If an exponentially growing solution is possible, then it's not zero stable. If an exponentially growing solution is not possible, then the scheme is zero stable. Now, you can show local order of accuracy and zero stability all without implementing the scheme on any differential equation. And once you have these two through the Dahlquist equivalence theorem, you know the scheme is globally accurate when it is applied to any differential equation. Is it clear the relationship between These three. Okay, global accuracy is what we want. This is what we want. What we want. Okay, and the zero stability and local accuracy is easy to analyze. And once we have the two easy to analyze thing, we check these, then we automatically know global accuracy. All right. So the relationship between these two are these three are this simple. So when we have these two, that leads to global accuracy. All right. So we discussed zero stability, but zero stability is a pretty weak criterion, right? A zero stability means it can solve dUdt equal to 0. Yes, if a scheme is locally accurate and zero stable, we are going to have global accuracy. But sometimes global accuracy may not be enough. I'm going to show you an example why global accuracy is not enough. So global accuracy only says that when delta t equals to 0, my numerical solution converges to analytical solution, right? It doesn't say anything on if my delta t is finite, how big the error is, right? It also doesn't say how smooth my solution is, right? And it turns out we can get really horrible numerical solutions for finite delta t, even if a scheme is local order of accuracy and zero stable. I'm going to show you such an example. The example is using a second order accurate scheme and also zero stable. Can you guys think of a zero stable scheme that is second order accurate? What scheme you've learned that is midpoint? Exactly. Midpoint is locally accurate, it's zero stable. And it's something we implemented last lecture, right? So let me go back to my Dropbox. Let me get a little bit bigger. Okay. What? Oops. What do I have? Wait, where is my shared folder? Okay. Sounds like it's up there, but like. Okay, it's over here. Okay. I want to ask you who have completed these implementations we started last class. Of course, those guys here have finished, right? Who else did it? Can you raise your? No, not including midpoint. Great. So we have a bunch of people who did this. Anybody willing to try their code on? Willing me to try their code here? Oh. I mean, I can. Yeah. My midpoint. Your midpoint. What's? Okay. The first two. All right. So I'm going to copy your code into today's folder. All right. And which one should I run? Ballistic. Okay. Thank you. Okay, ballistic. Right. So I see you did forward order. You did forward order and do midpoint. Okay, you are also doing this. So I'm just going to use. I see you did this double percentage thing. Does everybody know how to use that? Yeah. So basically, split the file into sections. So I can do. I think it's Control Enter, right? To just run this section. I think it's already done, and I can run midpoint. All right, I get a trajectory, right? That's nice. What if I change the delta t to 0.5? Okay, what if I change delta t to 0.5 and I'm going to close all? in the beginning of this, so that like I'm going to close my last video. I'm going to run it again. Ouch, I get this. So what happens? Okay, and this doesn't actually defeat the purpose, so it defeats the analysis of the scheme being globally accurate, right? The scheme is still globally accurate because as I decrease my delta t, as I make delta t equal to 0.3, for example, the oscillation gets smaller, right? My solution gets better. If I decrease to 0.2, the solution gets still better. You can still see this goes going on, but it gets better and better. And when I decrease it to 0.1, I mean, it's almost invisible. But I'm going to show you, if I let this thing drop further, the oscillation is going to show up. You want to try? You want to try? Okay. T is equal to 100. Let's see. If T is equal to 100, oh, you did the Y-lim thing. I'm going to remove the Y-lim and do axis equal. That's too much. T is equal to 50. What? Okay. Did I change anything? Why do I get this? Do I need to do this again or not? Why do I get a clear all the variables? Run the first one. Okay, I ran it, and then run the midpoint. Oh, there it is. All right. So let me go back to my t equal to 50. You see what I get over here? Right? I don't get a solution that is smooth. I get a solution that that's how my ball drops down here, goes back a little bit, goes down, goes up a little bit. It does this. See? So what happens? I mean, still, it doesn't defeat the purpose of being globally accurate. If I make delta t equal to 0.05, this oscillation becomes smaller, right? You can still see it, right? But it becomes smaller. But like when I increase t to be 100 again, this is going to show up again. I mean, I see something is wrong. But like okay. So I'll do that later. But the point is clear, right? Although a scheme is zero stable, it is second order accurate, the midpoint scheme. But it doesn't really give the desired behavior. It's even worse than the forward Euler, which is only first order accurate. If you look at the forward Euler with the delta t of 0.5, which shows horrible behavior for midpoint, right? I get an error somewhere. Oh, I need to run this first and run this. So yeah, forward Euler works fine with the delta t equal to 0.5. You see. So in this case, forward Euler actually works better than midpoint, even though midpoint is a second order accurate scheme. So why is it the case? Both schemes are zero stable, right? Midpoint is more accurate, supposedly more accurate than forward Euler. But applied to this specific equation, unlike the equation we saw last week, the pendulum equation, on the pendulum equation, midpoint actually works much better than forward Euler for large time steps. Here, forward Euler works better than midpoint for large time steps. The reason is linked with eigenvalue stability. Okay, it turns out that the particular case we are looking at, for which forward Euler is actually eigenvalue stable, and the midpoint is not eigenvalue stable. So eigenvalue stability is a requirement that is more strict, more stringent than zero stability. Although midpoint is zero stable, it is not eigenvalue stable for that particular equation. Okay, any questions? Before we...
For that particular equation, so this varies not just by scheme, but by which differential equation you're solving.
Exactly, good question. So zero stability is per scheme, right? A scheme is either zero stable or not, right? It's independent of differential equation because it just tells you can the scheme solve this trivial differential equation or not. Eigenvalue stability, on the other hand, depends not only on the scheme but also on the equation. In the simplest case, eigenvalue stability looks at, are you able to solve this equation? So you can see zero stability is like a special case of eigenvalue stability where lambda is equal to 0, right? So a scheme, if a scheme is eigenvalue stable for lambda equal to 0, then it is zero stable. But a scheme being zero stable doesn't mean it is always eigenvalue stable for all differential equations like that. Okay, so let's start discussing eigenvalue stability. And at the end of the lecture, I'm also going to start talking about implicit schemes and the Newton-Raphson iteration. All right. So eigenvalue stability analysis, the first thing I want to show you is this link. If you go to this link, which I already opened, I think, you're going to get to the website called mathlist.org, and it hosts a bunch of what we call math lists. They are basically Java app lists that like allows you to visualize these various things. And if you click on it, it is going to open a window. You need to set your like a Java security or something like add an exception to mathlist.org. Otherwise, your browser may actually block the thing. But once you have it, let me make it full screen. F11. Okay. Right. So what it shows you is for what lambda. Remember, we are talking about eigenvalue stability. A scheme is a scheme stable or not for this equation, right? So we have a lambda here. Lambda in the method, lambda can not only be real values but complex values. So this is the space of lambda times delta t. So you can think of a point here is 1, 0. That means lambda times delta t equal to 1. So for example, at this point, if lambda is equal to 10, delta t is equal to 0.1, then you are at this point. If lambda is equal to -1, delta t is equal to 0.2, then you are at this point. Okay. The blue region here shows you that for what values of lambda, for what combination of lambda and delta t, actually it includes the lambda times delta t, for what lambda times delta t is a particular scheme eigenvalue stable. So here is the forward order. For forward order, the scheme is stable only if lambda times delta t lies within this very small circle. Okay, what does this mean? This means that if you have a lambda greater than 0, would forward order ever be stable? No, right? Actually, in this case, I would expect if lambda is greater than 0, even the analytic solution of the PDE is unstable. Why? What is the analytic solution of the PDE? E to the lambda t, right? E to the lambda t is the analytic solution of the PDE, is unstable by itself. All right, so actually not only on the real line, but also the whole right-hand side, the analytic PDE, the analytical ODE is unstable, right? Because if a lambda is here, let's say lambda is 1 plus I, how does the solution look like? It's an oscillatory growing solution, right? The imaginary part determines the frequency of the oscillation, but the real part determines the rate of growth. As long as the real part is greater than 0, it's a growing oscillatory solution. All right? So that means for the whole right-hand side of the complex plan, the analytical solution of the ODE is unstable. So you shouldn't really expect a numerical scheme to make it stable. I mean, you're going to see some numerical scheme actually do make some of them stable, but like you shouldn't expect it. What is more intriguing is that even on the left-hand side plan, okay, for which the analytical behavior of the ODE is either just a monotonic decay. I mean, if you are on the real axis, e to the like something negative times t, right? So if du dt equal to negative lambda times u, the solution is u equal to e to the negative thing times t, right? So you get a monotonic decay. If you are over here, you have a negative real part and a non-zero imaginary part. Then you have an oscillating and decaying solution. So you would also expect it to be stable. But forward order actually is only stable within this region. If you have a point lambda delta t over here, it's unstable. Right? Okay, so that is interesting. I'm just going to do a very brief analysis of showing why that is the case. Forward order, v of n plus 1 minus vn over delta t applied to f of vn, which in this case is lambda times vn, right? Okay, so let's move all the knowns to the right-hand side. So this term is known, this term is known. So move this to the right-hand side. We have vn plus 1 over delta t is equal to vn plus delta t over delta t plus lambda times vn. And collect term is if we collect terms, vn plus 1 would be equal to 1 plus delta t lambda times vn, right? We can easily see if lambda is greater than 0, we have a growing solution, right? If lambda is greater than 0, this term is greater than 1, we grow. What if lambda delta t is less than minus 2? We get an oscillatory growing solution, right? Because 1 plus delta t lambda would be less than minus 1. And the next iteration, I'm going to get a solution of the opposite sign, but larger than what it is at the nth time step. That is why forward order is unstable when we have a lambda delta t less than minus 2. Same thing happens when lambda is imaginary and lambda 1 plus delta t lambda has a modulus of greater than 1. We are going to, that means we are outside this circle, we are unstable. All right. So that's how you do eigenvalue stability analysis. You plug in f of u equal to lambda u into the differential equation. You left all the terms that is vn on the one side, all the terms that is vn plus 1 on the other side. And in general, you plug in the solution that is exponentially growing to see if this discrete scheme allows an exponentially growing solution. All right, that is how you would analyze eigenvalue stability, similar to how you would analyze zero stability. Any questions?
The value that has to be less than 1.
Yeah, the absolute value of that thing has to be less or equal to 1. Yes. Yeah.
So when you said that the oil has to be less than minus 2,
Mm-hmm.
what lambda is less than minus 2?
Lambda times delta t is less than or equal to.
Okay.
Yeah.
So is that just kind of something you have to check for every time? Like, how do you know minus?
Okay, good question. When you are implementing forward order on a real thing, how do you know whether T lambda is less than minus 2 or not? It's a good question. So most of the time you can analyze the eigenvalues. Let me back up. Let me say, if you look at a scalar differential equation, if you look at like just one single differential equation, not a coupled system of differential equations, even if the equation is nonlinear, you can usually linearize the differential equation and look at what lambda is for the linearized differential equation. And the key is not to manipulate lambda, but ensure that delta t is small enough. All right. So let's look at here. Imagine, this one is lambda delta t, right? But imagine your lambda is taken over here. If your lambda is, let's say, minus 3 plus 4i, can forward order be stable? No. If my lambda is here, can forward order be stable?
No.
We still have delta t, right? What if lambda is here, what if you make delta t equal to 0.1? Then lambda times delta t would shrink way over to here, right, into the stability region. And we are fine, right? Okay, what if lambda is minus 500 plus 1,000 times I? Yeah, even if lambda is minus 500 plus 1,000 I, if you make the delta t equal to 0.0001, you're going to be fine, right? You're going to shrink your eigenvalue times delta t into here, and you're fine. Okay, what cases are not fine? What are the cases where no matter how small you make the delta t, you are going to be unstable? Right, if lambda has a positive real part, if lambda is over here, then no matter how small you shrink it using a small delta t, because delta t has to be real, right? The concept has to be real. You're going to shrink it to over here, but it's still unstable, right? Okay, what are the cases would forward order not work? Yeah. If it's just an oscillation, if the eigenvalue lambda is just a pure imaginary value, right? It's a non-decaying oscillation. So if the analytical solution is a non-decaying oscillation, just like what we had on lecture 2, like the pendulum, right? If we have a pendulum that has no density, forward order would never be eigenvalue stable. And that's what we saw, right? And even when we made delta t to be small, it's still mildly growing. All right. So yes, forward order wouldn't work if you have a positive real eigenvalue, or if you have a zero real eigenvalue. Otherwise, you can always shrink your delta t so that the scheme is stable. Let's look at another scheme, midpoint. Okay, what happens on midpoint? What is the stability region of midpoint? It lies exactly on the imaginary axis, like from minus I to I, right? So the case we just analyzed, saying pure oscillation would never work for forward order, would never be stable for forward order. It works perfectly fine for midpoint, right? That's why when we did the pendulum case, midpoint worked so well. All right, it was like amazingly better than forward order. But when we apply it to this case, forward order works better because try to guess where the eigenvalues are for the case we had on the cannonball. Anybody wants to take a guess of what lambda is for that problem? Hmm? Something with a very small imaginary component. Heavily damped means you have a negative real part, right? If you look at midpoint, as long as the eigenvalue lambda has a non-zero real part, then it wouldn't be stable, right? No matter how small you make delta t, you're gonna, I mean, if the eigenvalue is here, or here, no matter how small you make delta t, you're gonna shrink it towards the origin. But no matter how much you shrink it, you will never be exactly on the imaginary axis between minus and I, right? So as long as the solution is not purely oscillation, it's not pure oscillation, midpoint wouldn't work. All right, so forward-Euler and midpoint are like two schemes that have complementary values, but they never overlap, right? I mean, an equation would either work for forward-Euler or it'll work for midpoint with a small enough time step, right? If the lambda is exactly on the imaginary axis, with a small enough delta t, you can make midpoint work. If it has a negative real part with a small enough time step, you're going to make lambda times delta t into this region. Well, we are not concerned about if lambda has a positive real part because the differential equation itself is unstable and we don't want to solve it anyway. we don't expect it to be stable. Yeah, right. So we don't really expect our scheme to be stable. If it's stable, then it is artificially stable because the real solution is going to be unstable. Backward Euler, because, okay, we can see that for any differential equation that is actually stable, backward Euler is stable, right? The blue region is anything except for this. No matter how big delta t is, you can make delta t equal to 1,000 if you like. Backward Euler is the argument stable. Okay. So even in this region where the real differential equation is unstable, it artificially makes the solution stable, which actually gives you a wrong answer, but like it's stable. All right. Trapezoidal rule. That is like, yeah, you said that's what we want because if you look at the stability region of trapezoidal rule, it is exactly the same stability region as the analytical ODE. It doesn't always mean you're going to get the expected behavior because you're going to see if my lambda delta t is over here. The rate of decay of the trapezoidal rule versus the real ODE is going to be very different. But like at least in terms of stability region, it is exactly what you have for the analytical ODE. And the Runge-Kutta schemes is something you are going to learn later on for this week's reading. But you're going to see these weird shapes, right? The Runge-Kutta schemes are explicit schemes. So for nonlinear differential equations, you're going to see very soon that explicit schemes are a lot easier to implement than implicit schemes. And for example, Runge-Kutta 4 is great because it has the advantage, it combines the advantage of forward Euler and midpoint. Why? Because as long as my lambda has a non-positive real part, I can make delta t, as long as I make delta t small enough, I'm going to get into the stability region, right? Forward Euler requires me to have a negative real part. Midpoint requires me to have a zero real part. From the color 4 requires me to have either 0 or negative real part. And I can make delta t small enough, it is going to work. All right. Questions? Yeah.
So you take the individual formulas, so like say RK4, and then you compare that to the analysis. That would. So
What I'm eigenvalue stability concerns about a equation that is dx dt equal to lambda x, right? We are looking at if I apply the scheme with some delta t to this equation, am I going to get a growing solution or I'm going to get a stable solution?
Is there a way to figure out, say, you have the solution, say, as long as it's or is it you have to do it and then figure out
the stability region is different for each scheme.
okay.
So you have to, yeah, it's separate from the analytic solution. For each combination of scheme and lambda delta t, you have an answer of yes or no. Okay. So
what's important about the analytic solution is eigenvalue. It's not the analytical solution itself, it's the eigenvalue. It's the nonlinear problem you realize in concept and eventually eigenvalue go somewhere in the not physical space. It's eigenvalue is
Oh, that's good.
The nonlinear problem is to figure out eigenvalue, and then you know that you can combine a certain scheme with a delta t, eigenvalue for a solution. The nonlinear problem, eigenvalue for the eigenvalue for so it's the eigenvalue of the problem. It's the physics of the problem.
yes.
Do you ever run into a situation where you start with a nonlinear equation and then you linearize it, but because of your error that you created, not when you linearize the equation, this sort of method lies to you, and you think you should be stable with a certain lambda delta t, but you're not actually because of the linear relation?
That's possible. I don't have a definite answer to that, but it's possible. And what I want to emphasize is that if you linearize the equation and eigenvalue stability shows that it is unstable, then it's very likely when you apply to the nonlinear equation that it's going to be unstable. Right. So eigenvalue stability, I would say it's a good so before you apply a scheme to the differential equation, it's a good idea to check eigenvalue stability. And this also gives you a guidance of when you see something being unstable, right? Is it because you are using the wrong scheme, or is it because you have a too large of t, right? You can take a look at its eigenvalues and figure out which case it is. All right. Any other questions? Okay. Let me give you a challenge. Now, if I get two coupled differential equations like this, x equal to minus y minus epsilon times x, y is equal to x, where epsilon can range all the way from 0 to t. For what epsilon and delta t is forward order stable? For what values of epsilon is backward order stable, and for what value of epsilon is midpoint stable? I mean, not for epsilon, but for what combination of epsilon and delta t is each of the schemes stable? Form groups of 2 or 3, and figure this out. All right, a lot of you have got the answer or almost get the answer, and let me do it here to make sure everybody is on the same page. So first of all, the first step is to write the differential equation into a matrix form.
So I would give it
The d dt of x and y, let's write it in a similar way as du dt equal to lambda u. But here the lambda is no longer a number, it is a matrix, right? And what is the matrix? Just fill in the blanks. Dx dt minus y minus epsilon x. So minus epsilon x minus 1y. dy dt equal to x, so 1x plus 0y, right? Okay, so I get a matrix here. And how do I go from the matrix to eigenvalue stability? Take the eigenvalue, right? Take the eigenvalue. So the eigenvalue of this matrix. And I may be lazy, so let me do it in MATLAB. Okay. So for this 2x2 matrix, you can do it by hand, but like if you get a large matrix, what do you do, right? Okay. Yeah. Let me do the bad example and. Okay, I'm just going to make epsilon go all the way from 0 to 10, right? So length space is putting a bunch of epsilons. And the matrix here is going to be like this. So let me do this. Let me put a symbolic. Let me put e to be a symbolic variable, and the matrix is what? Minus e minus 1 1 0, right? So that's what the matrix is, and e means epsilon. And you can do the eigenvalue of this matrix. It gives you the formula which you guys have figured out, right? Minus epsilon over 2 plus or minus the square root of, to the half power is basically square root, right? Of this thing. So let me just again say epsilon e is equal to length space of 0, 10, 100, and I'm going to say lambda 1. The first eigenvalue is, I'm just going to copy the formula here and paste it. And I need to convert the products into dot and exponential into dot exponential, and everything else is going to be fine, right? I'm going to also look at the second eigenvalue. I'm going to paste it and also do the dot product and dot exponential. Okay, I have L1 and L2. Let me plot them. I'm going to plot a line and dot. So what you get is in the complex plane. Let me do axis equal. In the complex plane, I'm plotting the trajectory of lambda 1 as my epsilon goes from 0 to 10. I'm going to say hold on and plot the evolution of lambda 2. Actually, I want to plot it in a different color. Okay, so you get an evolution of lambda 1 going this way and the evolution of lambda 2 going this way. And remember, this is in the complex plane, the two eigenvalues, right? Okay, anybody remind me what is the stability region of forward Euler? Yes, a circle around -1. So a circle around -1, right? Going to the MATLAB plot, it's a circle around here, right? But remember, the stability region is a stability region of what? Of lambda t, right? Lambda times t. Well, here I'm just plotting the lambda. So what does that mean? If I have, let's say, epsilon equal to 10, one of my eigenvalues is here. Is there any hope I mean, the other eigenvalue is over here. Is there any hope of making forward order stable? By how? By a big delta t equal to how much? Or a small delta t? A small delta t equal to how much? Huh? Less than 1/10 is necessary. I mean, this is -10, right? As long as I can make this point within the unit circle centered on -1, where the extent to here is -2, right? So as long as I can have a delta t that is less than 0.2, I can make forward order stable. Right? Any questions on that? Yeah, right, sure. Okay, you beat me.
Reported to me for what's later. Just the case you're talking about, there's 99 sitting out here, basically -10, and there's one sitting in here, we're supposed to do. And we're asking the question, what data to make sure that lambda -10 comes out to t.
Yeah, right. Okay, thank you. Right. You have to make a, so these are the 2 points. You have to make a that is small enough for that tree group heading to the stability region. All right. So, question? Okay. And so you can see when lambda is very large, when epsilon is very large, it's difficult to, you have to have a small delta t to shrink into stability region. Another case is when epsilon is very small. Actually, at epsilon equal to 0, I get 2 eigenvalues equal to plus I and minus I. How can I make the case stable for forward order? I can never make forward order stable, right? I can make delta t goes to very, very small. These 2 points would shrink over here, but they're still on the imaginary axis. And remember, forward order, it doesn't include any point on the imaginary axis other than 0. So when epsilon is very small, it's very difficult. It's impossible to make forward order stable. And when epsilon is very small, it takes a very, very small delta t to shrink it into the circle. Okay. So when a system is slightly dissipated, it's like it's almost pure oscillation, but decays slowly. It also takes a lot of time step for very small delta t for forward order to accurately resolve its behavior. Yes.
For forward order, those eigenvalues have to be within the stable region.
Good question. Does both eigenvalues need to be in the stability region? Yes. Both eigenvalues or all of the eigenvalues, in this case it's 2 eigenvalues, if they have a bigger matrix, all of the eigenvalues have to be in the stability region. And the eigenvalues of a matrix aren't always conjugate to each other. I mean, in this case, only these portions are conjugate to each other. And as long as epsilon goes greater than 2 or something, they become on the real axis and they are no longer conjugate to each other. And if you have a bigger matrix, that's even more true.
You can kind of say physically why they're flipped, because the one that you're worried about, I don't know, I can imagine the way over and over, here that at minus 10 eigenvalues are doing numerical trouble. Because it decays so fast, you have to take a tiny time step to resolve. If you think about the major system is decaying really fast, it takes a tiny time step to resolve it. If you don't take a tiny time step, the numerical solution will be unstable. It's kind of the opposite. We're mostly about physically that numerical is kind of problem. We're going to take ones out and we'll see more of that in the physical expression of ones out of the real access out far for this. So we can problem.
Yeah, right. In instability analysis of the analytical system, the analytical system is stable for the whole left plane, right? So you are looking at the most dangerous one, which is closest to the stability boundary. When we have a numerical scheme, the most dangerous ones are not necessarily the one that lies towards the right. It may be the ones that lies most towards the left, right, or most close, most dangerous, most close to the boundary of the stability region. They are not necessarily the ones that is closest to the imaginary axis.
Yeah, so people call it adaptive time shifting.
Yeah.
We're going to see, I mean, you're going to see some other stability regions, like the temperature that we have to cover, and we're going to see implicit within. But for example, in human genetics, people like to use these kinds of methods that use adaptive time shifting, because it's different points in the reaction taking place, different times to overall. In fact, I believe networks are usually sized by exactly that. If you were to look at the aspects that come out, you see that they were the same stories.
Yeah, for nonlinear problems, sometimes that is extremely important to adapt the time step according to because at different place, at different parts of the solution, when you linearize the nonlinear equation, you get different eigenvalues, right? So when you get the big eigenvalues or dangerous ones, it's important to make time step small. Right. Any other questions? Okay, let me pose another challenge question. Oh, right. Okay. Yes. What about midpoint? If you look at the eigenvalues, would they work for midpoint? Only when epsilon is equal to 0, right? Only when epsilon is equal to 0, you get these two eigenvalues. And for what delta t would midpoint be stable? Less or equal to 1, right? Because the stability region for midpoint, when looking at lambda times delta t, is exactly going from this point to this point. If you make delta t less or equal to 1, then you're going to shrink this point towards into the stability region. If you make delta t greater than 1, you would push this point in the lambda delta t plot out of the stability region and it would be unstable. All right. Can you find a scheme where it would be stable for all of these epsilons? Trapezoidal, right? Because the trapezoidal rule has a stability region that covers the whole left plane, and we are looking at the whole left plane over here, right? What else? Huh? The squishy one is called the Rangapata form. Okay, that has a stability region somewhere like this one peanut or something like that, and you would you can have a small delta t, you would shrink the whole thing into the peanut, right? Okay, yes. How do you find the stability region for various methods? Good point. I have showed you how to find the stability region for forward Euler, right? I have showed you how to find the stability region for forward Euler by basically plugging du dt equal to lambda u into the scheme, right? I'm going to show you another example of doing this for midpoint. All right. Okay, if you have a midpoint, you have Vn plus 1 equal to Vn minus 1 plus 2 delta t times f of Vn, right? I can do this example, but you get to show me, you get to help me. What's next? When I analyze eigenvalue stability, what do I do next? What is eigenvalue stability? Yes, eigenvalue stability basically shows is the scheme stable for Fu equal to lambda u, right? So basically we're asking, is the scheme stable for this differential equation? So when we look at this as f of u, we get lambda times Vn, right? Okay, so I'm going to write it down again. This is what we want to analyze whether admits an exponentially growing solution or not, right? How do I analyze if it admits an exponentially growing solution or not? I'm going to try one, right? I'm going to try say Vn plus 1 is equal to V0 times z to the n plus 1, right? Vn equal to V0 times z to the n, and Vn minus 1 equal to V0 times z to the n minus 1. I'm just going to try an exponentially growing solution to see if it is possible for z to be something greater than 1 or less than minus 1, or having a complex value that has a modulus greater than 1. Right, if it's one of these cases, I'm going to get an unstable scheme. Okay, let me plug this in, and I'm going to cancel all the V0s. What I'm going to get is z to the n plus 1 power is equal to z to the n minus 1 power. I mean, these are time steps, right? These are time steps. Now, what I get is to the powers. I'm going to use parentheses to denote time steps, and the ones without parentheses to denote power. This is plus, sorry. Plus 2 delta t times lambda z to the n. Okay, what do I do next? Factor out z to the n minus 1, right? I'm going to get a quadratic equation equal to 1 plus 2 delta t lambda times z. All right. Okay, now I can get the solution for z to see if it can lead to a exponentially growing solution or not. So I believe I get 2 lambda delta t plus minus square root of 4 lambda square delta t square plus 4, right? Okay. So let me go put it up. Okay, so this is the z I got. I want this z, okay, to have a modulus less or equal to 1. Right? But if you look at this, okay, if you look at this part, okay, what do I get already? At least 2 divided by 2 if lambda is okay, so let's first see. If lambda is a real value, okay, if lambda is anything real and non-zero, then lambda squared is going to be something positive. And what I get is something greater than 4. When I square root it, it's going to be something greater than 2. All right? So, because I have a plus or minus, one of them is going to have a magnitude greater than 2. When divided by 2, I'm going to get something greater than 1. So for any real lambda, I'm going to be unstable. right? And you can also figure out for complex values of lambda, what values is going to make it stable, what value is not going to make it stable. And in fact, you can solve some kind of a inverse problem. You can solve for all the values of lambda delta t. That would make this z having a modulus of exactly equal to 1. So if z has a value exactly equal to 1, my scheme is going to be exactly on the boundary of stability, right? So if I have all the z's less than 1, I'm going to be stable. If I have one z that is greater than 1, I'm going to be unstable. If I have one z that is, if I have my maximum modulus z exactly having modulus of equal to 1, I'm on the boundary. So by solving that inverse problem, moving from a z that is modulus 1 to a lambda delta t, I'm going to compute the boundary of the stability region, which gives me something like this. So if I draw the boundary, if I trace the boundary, that gives me a z modulus 1. I'm going to plot its boundary of stability region. Yeah.
The way I would do it, is I would put d equal to I theta. Even I theta is a point that has one, that's what we're looking for, the boundary. And I would substitute into the z squared equals 1 plus 2 substitute and the z, so before the factorization. Then e to the I theta squared is equal to 2 I theta. It's going to be equal to 1 plus 2 delta t lambda e to the I theta. And then when you rewrite that, you can actually look, that's particular case, it comes out to be sine theta divided by 2 or something. And then you just theta goes from 0 to 2 pi, and you immediately see that we put it down here. That's a trick that works for a lot of these things. Just right. E equals e to the I theta, substitute it in, and now you have theta going from 0 to 2 pi, which is going on to the.
Yeah, Professor Willcox is saying that when you look at this equation and plug in z is equal to e to the I theta, you're going to get z squared, which is e to the 2 I theta, is equal to 1 plus 2 times delta t lambda times z, which is e to the I theta. Right, and then right, and you can figure out the stability boundary for delta t lambda using just taking this to the left hand side and this to the right hand side. Any questions? All right. Okay. Let me show one last thing. What if you have a du dt equal to minus u squared? Okay, we get a nonlinear equation, right? For what scheme this would be stable? What scheme this would be unstable? Analysis of this scheme lies in linearization. Okay, so let's say if I have a u of 0 at t equal to 0 equal to 1. Okay, what if I linearize this equation? What if I say u, I'm going to perturb a u to u plus delta u, or plus a very small v. Okay, what is the result of the linearization? The linearization can be seen by plugging both the u and the u plus v into the differential equation. If you plug just u, you get this. If you plug u plus delta plus v, you get du plus v dt equal to minus u plus v squared. All right, and here linearization v is very small. And because v is very small, you can derive du dt plus dv dt. This is just factorizing u plus v out of the derivative, is equal to minus u squared minus 2uv minus v squared, but because v is very small, this term is negligible. This term is very, very small, or very square small, right? Okay, now when you look at the unperturbed equation has a du dt, the right-hand side has a minus u squared, the right-hand side has a minus u squared. These two terms cancel out because of the unperturbed equation. The only thing you get is the linearized equation dv dt equal to minus 2u times e. Right? Any questions on this? No? Yes? No? Yes? That's how you would linearize a nonlinear equation, by perturbing the variable into the variable plus something infinitesimally small, and remove all the very, very small terms, and the very, very, very small terms, if you have a cubic term. Okay, right, so now we have the linearized equation, which is linear with respect to v, right? Can somebody tell me, if I use forward Euler, when would this scheme be stable? When would my forward Euler be stable? Good. This case, this is my lambda, right? I'm solving dv dt equal to minus 2u times v. My minus 2u is my lambda. This is where, like, you have a question on adaptive time stepping, right? This is when lambda actually depends on the solution u of the nonlinear equation. As I solve the nonlinear equation, my lambda of the linearized equation actually changes, right? So in the beginning, I mean, the solution of this equation looks like this. Actually, we figured out ut, I think, is equal to 1 over t plus 1 or something like that, right? In the first or second lecture, we figured that out. So in the beginning, u is large, and minus 2u is kind of on the negative side and big. We need to use a smaller time step. And later on, as u becomes smaller and smaller, we are allowed to use larger time steps for forward Euler to be stable, right? This is a case where we actually can benefit from adaptive time stepping, right? The case is minus 2u has to be less than 0, equal to 0, and greater or equal to minus 2, minus 2u times delta t, because I'm looking at lambda delta t. All right. This is the stability for forward Euler. Questions on this? Is it clear? How did I linearize this and apply eigenvalue stability? All right. Okay. Now, the last thing I want to do. Not sure I have time, but like I am going to pose this as a question. Is how do I apply backward Euler on this problem? How do I apply backward Euler on this problem? What is backward Euler? Can somebody help me write down what backward Euler is? Okay, what backward Euler is? What forward Euler? What is forward Euler? If I use forward Euler, what would it be equal to? Forward Euler would be f of u to the n, right? What would backward Euler be? Huh? For f of un is forward Euler. Yeah, backward order is f of u to the n plus 1. All right, so that is backward order. And in this particular case, I'm going to get minus un plus 1 squared, right? I'm going to get an equation that looks like this. How do I solve that equation? If I get any answer that is good, I'm going to end this class. Okay, un is known, right? I'm at the nth time step. So the un is known. Let me put unknown in red, un plus 1, and the known in blue. Okay. Yeah, that makes it a quadratic equation, right? We get an unknown square, linear term, and a constant term, right? So we can see we need to solve a quadratic equation now in order to go from one step to the next step. All right? We need to solve, in some sense, a nonlinear equation to go from one step to the next step. And what if this is cubed? Then I need to solve a cubic equation. What if it's fourth? I need to solve a what equation? Quadratic equation. What if this is sine of u times exponential of u? So this is what we are going to be reading from now to Monday. You're going to be reading about one of the most important techniques in numerical analysis. That is how to solve a general nonlinear equation like this. Something that is even more complex than a quadratic equation, more complex than a cubic equation, something that you may not have an analytical solution. And it is extremely useful in time stepping of nonlinear equations, such as encountered over here. Okay, so I will see you on Monday.